PCR is an absolutely incredible tool in molecular biology, but let's be honest, getting it to work perfectly can feel like, well, like a dark art sometimes. Today, we're going to pull back the curtain and look at the tiny, elegant molecular events that make the difference between a total failure and a flawless experiment. So, let's dive in. Okay, so what is a perfect PCR? You know the kind I'm talking about, a single super bright band on the gel right where it's supposed to be? Well, it all comes down to finding that one, precise, almost magical set of conditions where everything just clicks. But how on earth do you find it? So the first hurdle we've got to clear is optimization. PCR is just incredibly sensitive. The temperature, the amount of stuff like magnesium chloride in the tube, if you're off by just a little bit, the whole thing can just fail. We have to find that perfect sweet spot. And this is where a super clever technique called gradient PCR comes in. Instead of running, dozens of different experiments one by one, you test a whole grid of conditions at the same time. This machine, the thermal cycler, actually creates a range of temperatures across the block, from hot on one side to cooler on the other. And you just know, somewhere in that grid is our perfect condition. And this really shows you just how picky PCR can be when it comes to temperature. We're talking about the annealing step, where our primers have to find and stick to the DNA. If it's too cool, your primers just get sloppy. They start sticking to all the wrong places and you end up with a mess. But if it's too hot, they can't even hang on. You get nothing at all. So it all boils down to this, finding that Goldilocks zone. That one single tube where the temperature and the magnesium are just right. When you find it, the primers bind exactly where they're supposed to, and that sets the stage for that beautiful, explosive amplification that we're all looking for. All right, so we've nailed the conditions. The reaction's running perfectly. But how do we actually see the DNA being made in real time? Well, that brings us to our second big molecular event, making our DNA actually glow. Let me introduce you to CyberGreen. This little molecule is basically a molecular light switch. When it's just floating around by itself, it's dark. But the second a new piece of double-stranded DNA gets made, CyberGreen slides right into the groove, it's called intercalation, and bam, it lights up with this bright green glow. More DNA equals more glow. It's simple, it's elegant, and it works. But wait a second, there's a catch, and it's a pretty big one. CyberGreen, well, it isn't very picky. It will light up when it binds to any piece of double-stranded DNA. So that forces us to ask a really important question. Is every single thing that's glowing in that tube actually the DNA we care about?
Yeah, this gel right here tells you everything you need to know. See those bands down at the bottom? That's junk. It's primer dimers, basically short bits of DNA made when primers just stick to each other. And because they're double-stranded, CyberGreen makes them glow too. It's basically creating a bunch of false positives, junking up our data and making us think we have more product than we really do.
Okay, so how in the world do we separate the good stuff from the junk? Well, we use this really cool trick called melt curve analysis. The idea is simple. We slowly heat everything up, and because different pieces of DNA have different lengths, they'll melt or fall apart at different temperatures. And would you look at that? The results are crystal clear. On the left, a perfect, clean reaction. You get one sharp peak at a high temperature, that's our target product. But over on the right, that's a messy reaction. You see two peaks. That first little bump at a lower temperature, that's your junk, the primer dimers melting apart really easily. The second, taller peak is our real target. This is how you can instantly tell if your signal is pure. Okay, for our last act, we're upping the ante. What if you need to be absolutely 100% certain that you are only detecting your target sequence and nothing else? For this, we need something with sniper-like precision. We need the TaqMan probe. Now, the TaqMan probe is it's a beautiful piece of molecular engineering. It's a special little piece of DNA that's designed to stick only to your target. On one end, there's a reporter dye that's just dying to glow. But on the other end, there's a quencher, and it acts like a tiny black hole, literally sucking up all the light from the reporter as long as they're stuck together, so the probe stays silent. And this is where the magic happens. It's like a tiny molecular drama unfolding. As the Taq polymerase chugs along, making new DNA, it runs right into our probe. And when it does, it activates a special power. It's exonuclease activity. It just starts munching on the probe, like Pac-Man chewing through the dots, and completely shreds it. And in that moment, the reporter is suddenly free. It's released from that quencher, and bam, it lets out this brilliant flash of light.
You get one perfect flash of light for every single copy of your target DNA and nothing else. I mean, that destructive power of the polymerase is the whole key. The way the source material put it is just perfect. It's pretty much eats DNA for lunch. That targeted destruction is what guarantees, with absolute certainty, that you're only seeing the signal you care about.
So there you have it, from the wide net approach of gradient PCR to the simple glow of CyberGreen and its clever melt curve check, all the way to the absolute precision of the TACMan probe. Each one is a tool that solves a very specific problem. So the real question for you is, when you're back in the lab, facing your own challenges, which one of these amazing molecular tools is going to be the right one for your research?